Firstly, we'll start by the covariant derivative for the double integral. We have that is equal to the directional derivative, which is plus hij and the Gauss map. And for this one, by definition, it is we have the Christoffel symbol. Next, we try to express the Christoffel symbol in terms of the first fundamental form. Firstly, we have that the first fundamental form and we differentiate both sides with uj, which gives ul. It is and in the next step, we use this formula to insert into this one, which gives plus HIL, the Gauss map. Because Gauss map is perpendicular to the all the tangent vector, so that their dot product is 0, so that we have only these two, and with this it gives G K J plus GIK, so we have this formula, and in the next step we will cycling I, J, and L, so that we have the next two I, J, and L. G, J, L, J, G, L, K. Yeah, so we have 1, 2, and 3. And as we know that the first fundamental form is symmetric in the 2 index, and also for the Christopher symbol, it's symmetric in the 2 lower index. So that we can have, we want to have this term, which also expressed here. So we use 2 plus 3 minus 1, and it gives, on the left side, it is GJL minus GIJ equal to 2 times for these two. And for the other term, this one cancel with this one, because this one cancel with this one, because the index here are the same and the index here are the same. And wait, where's the problem? Oh, this is 3. And these two are the same, so it cancels out. And these two are the same. J, K. Yeah, this is J here. These two terms are the same, so these two cancel off, and we have this one. Next step, we multiply the GLK on both sides. With the GLK on both sides, this term vanish, and put the 1/2 here, and it gives this one. So then now we have the formula for the Christopher symbol. Christopher symbol here, it is this one. In terms, it only depends on the first fundamental form. And next, we want to prove the Gauss theorem, the Gauss equation. We start with, for the Gauss equation, we still start with this equation here. We differentiate that with another UL on both sides. B plus B plus HIJ V U L. Yeah, so here we first deal with this term, this one here. This one here we use the same formula again, which gives IJ H K L. This term. So yeah, this term is equal to this one, and for this term, because the Gauss map is perpendicular to the tangent space, so that its derivative is in the tangent space, which means the derivative of the Gauss map is the derivative of Gauss map here. It is equals minus Hij HQL FUQ. Yeah, so this is the. Now we sum up the term. We want to divide into two parts. One is in the tangent space and one is perpendicular to the tangent space. So here we change the K to Q. We change that K to Q here, so it is IJQ.一点水都没有啊。IJQ IJUL plus this term KIJQJKL and there's another one is minus HIJHQLUQ. So this is a term in the tangent space, and there are other terms. This one is just the H and this term plus. So this term is in the Gauss map, and we will neglect it in the following one. So now here, we should note that we use the fact that the 3 times derivative, it is the same as U, I, U, L. We change I and L, it is still the same. So we have here we change I with L, so it is plus K I with L and also we can extend this one. This one is G. We want to put it down, so it is G Q. Let me see. So this one it could be GQI HIL, and this one is let me just put this one. This one is GQL HIL. Yeah, so we will use the fact that the part in the differential in the tangent space is equal. These two terms are equal, and of course the two terms with the Gauss map are equal, but we won't use it in this part. So by these two terms are equal, we derive that HQ Qij here, UL minus QLJ.他们这该买新笔了，我已经受不了。UI, is minus m plus is equal to So this is the equation we got, and for the next step we want to multiply it. Okay, so we will first change the term like here, because all the index are double, the Q and L are double. Wait, let me check. Oh yeah, sorry, here we shouldn't use the same index. I think here we will use K. There's a mistake here. Here we will use QK, and so it becomes KL. And for this one is the same, we use QK, and this one becomes IK. Yeah, so here it is HIK, GQK, HKL. This one is GQK. So in the next step, we multiply two sides with GQK. We multiply two sides with GQK and we sum them up. So the one we eventually got, we don't need to do that. So the one we finally got is GQK JL HKL minus HLJ HIK. Here is the Gauss equation. And we can denote this one as RIJLQ, which is just the Riemann tensor. So next we are ready to prove the theorema. I don't know how you pronounce. Yep. So G, Q, P, Q, Q. So firstly we will multiply the two sides with a G, PQ. Maybe G, PQ. Yeah. So we can, firstly, we need to notice that the Christopher-Simon form is only depends on the first fundamental form, so that the whole left-hand side of the equation of the Gauss equation only depends on the first fundamental form, so that the right-hand side can be totally expressed only by first fundamental form. So now that we have this one is, we can denote it as Rij. So we now have RQIJL is equal to this part, and we multiply two sides with GPQ, and we sum up the Q, GPQ. We sum up the Q, so this one becomes so this one only is 1 when K equals to P, and we get JL K when K equals to P, PL and HL J HIP here. And then we will use IJLP. It works for all IJLP, and we will take it as 1 this one is 2, and we take it as 1 2 2 1, and it gives G 1Q G1Q G1Q R Q 1 2 2 is equal to R JL. Oh, sorry. It is as J is 1 2 1 2 1 JL. Wait a second. Oh, it's not wrong. It's 1 2 2 1. Yeah, it's correct. So this one is G. It's so strange. Wait, let me see. I think there's a mistake with 2L in the same part. IJKL, IJKL. Oh, the first term is GIJ. I wrote it wrong. This one is GIJ. Yeah, that makes it correct. GIJ. Yeah. Why I wrote it all again? It's GIJ. So we took it as 1 1 2 2. 1 1 2 2. So IJ here is 1 1 it is in the dimensional 3, which is just the determinant of the second fundamental form. So that we have shown that the determinant of the second fundamental form is this, which only depends on the first fundamental form, and then the Gauss curvature, which is this one, divided by this one, is the that hash is completely determined by the first fundamental form, and so is that G. So we can prove that the Gauss curvature in the dimensional 3 can be expressed totally with the first fundamental form. Yeah, okay.